let's go through what series and parallel circuits are all about. So let's start with this series circuit. Okay. So what's the number one characteristic of a series circuit? Hopefully what you saw in the last video and through the lab is that it's a string of connected resistors, right? But most importantly, there is only one path around which current can flow. And that one path means that all of the elements in the series depend on each other. That's why when I unscrewed any one of the light bulbs, all the rest of them went out, because there wasn't a complete path. We said to make a circuit, you need a complete path, and all those resistors were dependent upon each other. So just to draw what's going on there. So let's say I have a series circuit that looks like this, R1, R2, R3, boom, boom. So a couple of things to say here. So my electrons are flowing around. Notice if the electron goes through the battery, then goes through this, then through this, then through this, back, picks up more energy, drops off energy, drops off energy, drops off energy, right? So the important things here with a series circuit are the following. We have that each electron visits every circuit element. Another way to say that is each gets the same current, right? It's got to be the same because there's only one path, so everyone's got to visit everyone. Now, here's the big thing with series circuit is, so the battery supplies a certain amount of energy per charge, right? So when the charge goes through here, it picks up a certain amount of energy. With my 6-volt hobby battery, that's 6 joules of energy. And then what happens is it distributes the energy to the various resistors, okay? Now that doesn't mean that they're going to get the same amount of resistance. I'll go through that in a second, but what's going to happen here is the resistors split the energy, right? Because every electron's got to go through each of them, so each of them get a little bit of energy. You can kind of think of this as houses on a postal route. The mail person picks up mail, drops off some mail, drops off some mail, drops off some mail. Well, which house would get the more mail? On this analogy, the largest house would get the most mail, probably, right? Same thing here, the larger resistor ends up getting more of the energy, right? With the larger resistor getting more energy. Now, here's something else about series circuits. Looking at this, if I were to add additional resistors, right? So in other words, here I had 3 resistors in series with the battery. Let's say I had 4 resistors in series with the battery. What ends up happening here? Well, notice this battery is still the same battery. Like if it was a 6-volt battery before, it's still 6 volts. But now, rather than having 3 things splitting up that energy, I now have 4 things splitting up that energy. So now each resistor gets less energy because it has to be split more ways, right? So if I have a pizza and I'm trying to share the same pizza with 3 people, everyone gets a certain amount, the bigger kid gets the most, right? And then if I'm sharing that same pizza, same battery, with 4 people, everyone's probably gonna get less. Still, the largest of the kids gets the most pizza, the larger the resistors gets the most. So that's what's going on there. So you have to be very careful when you're wiring things in series, because the longer your series, the more you're distributing that same amount of energy over more things, right? But sometimes you want everything to depend on each other, right? For example, a light switch is in series with, say, for example, a light, because you don't want to have to unscrew the light bulb in and out every time you want to turn the light on and off. You want to go over to the wall and flip the switch on the wall. And because it's in series with it, that creates a dependency where you can turn circuits on and off based on that. Same thing like a dimmer switch. That's what a dimmer switch is. If one of these things is the dimmer, by controlling how big this is, right, like I can make it really, really big resistance, that means that it would get a greater share of the energy, and then these things would get less. If these were light bulbs, then they would become dimmer, right? So series circuits have definitely some applications there. All right. It also should be noted that the more things I have in series, the greater the overall resistance is, right? Because there's more things resisting the path. All right, let's talk now about parallel circuits. Well, what was the main feature of a parallel circuit? Unlike the series circuit, this had multiple independent pathways, right? We saw that when I took away one of the bulbs, the other bulbs didn't go out because they were independent of the first one. So multiple independent pathways. So sometimes let's just draw that, right? So I can draw them on their own loops like this. It's gonna get awkward, right? And so negative, positive, say that's my 6-volt battery, R1, R2, R3, and they each independently get their own current. Now, that's awkward. We tend to not draw it like that. We tend to draw these circuits looking like this. Where we have it together for a bit, and then it kind of splits. You can almost think of this as like a power strip, right? Like you have the line from the wall, and then it splits up into the individual branches, right? And that's what these things are called. They're called the branches of the parallel circuit, okay? And so I1, I2, and I3, and then I'm just gonna call this IT, okay? So multiple independent pathways. Here's the weird thing about the parallel circuit. If I'm talking about any given electron only visits one resistor per loop, right? Because they're independent paths. So that means that each resistor gets its own current independently of the rest. That means that every time you add, right, if you add an additional branch, you add more total current that flows, right? Unlike in the series circuit where the battery is the same thing, so that if you add more resistors, you have to split up that voltage amongst each. Literally here, every time you create a pathway, the electrons in the pathway start flowing, so you just have more charges flowing, right? And so that actually creates some danger, because notice here, these three currents all flow and become the overall current here. If I were to add a fourth branch, there'd be 4 currents flowing into this. You can kind of think of branches in parallel like tributaries of a river. They all flow into the main river. The more tributaries you have, the larger the total flow. This is actually super important for you to understand this. That's why it's dangerous to plug in too many things. Each time you plug something into the wall outlet, you are creating a branch in a parallel circuit. If you have too many things plugged in, that means that there's too much current flowing through the main wires of your house. And what happens when you have a lot of current flowing through wires? They get hot. They get really hot, they catch on fire. That's what causes electrical fires, folks. So we have to be very careful about adding branches in parallel because each branch gets its own current and those currents add up. Now, here's the other weird thing. Because each branch is independent, each resistor gets all of the energy each charge transports. So unlike in the series circuit where the resistor had to visit each of the three resistors, therefore had to drop off energy, drop off energy, drop off energy, coming here, this electron would drop off all of its energy, then go back, pick up more, drop off energy, right? These don't have to share voltage. Don't share voltage. Okay, so in a parallel circuit, each gets its own current, and they have to share. They don't share that current. All those currents combine into forming the overall current, and each resistor gets the total voltage, or they get the same thing as what the battery voltage supplies. The number of joules per coulomb is the same for each of these. That has a weird effect, right? So therefore, as you add resistors, we said the overall current increases because I added additional branches, right? Therefore, what happens is the effective resistance of the circuit decreases because we defined resistance as like this idea of not allowing current to flow. And so if something is allowing more current to flow, that must mean less resistance. So oddly enough, in parallel, adding branches adding resistors on branches, adding additional branches decreases the effective resistance, which is the opposite of what happens in series. If you add more things in the series, the overall resistance increases, okay? One last thing to talk about this. Let's say if I have 3 branches and I have 3 light bulbs, which would be the brightest? Which would get the most current? Well, in our lab, we saw that they had equal brightness. That was because they had equal resistance. They were identical light bulbs. But not everything in parallel gets the same amount of current. They get the same voltage, but what happens here is different pathways will get different amount of current. So which pathway would get the most current? And you may have heard a saying before that current or water things tend to follow the path of least resistance, right? The path of least resistance actually gets the largest current. So if I had 3 paths, one with a small resistance, one with a medium resistance, one with a large resistance, the small resistance pathway would have the largest current, and the one with the largest resistance would have the smallest current, right? In fact, the lower the resistance of a path, the greater the current that goes down that path. You may have heard of something, this is the last thing I'm going to say here, called a short circuit. A short circuit is what happens when you have a nearly zero resistance path. So instead of connecting in a device, you connect in a low resistance path by accident. Usually the way that occurs is something melts within the device that you're doing. And so rather than going on the entire loop of the branch, it kind of like, rather than going on this long thing, it kind of like shorts between here and here. And so you actually have a very short path for that to go along. And what happens is you get a massive amount of current, which tends to fry things. So short circuits are very dangerous in terms of that. So there you go. The last video that we will look at on Monday, we'll talk about safety devices to protect us from things like having too many things in a circuit, in a parallel circuit that causes too much current, and what happens when you get short circuits to present electrical fires.